So the next talk will be given by Catarina Tiburzi from the National Institute of Astrophysics in Rome about exploring the massive black hole binary merger with PTA.
Thanks. Have you said the Rome? Oh, no, sorry. No.
I thought you were in Rome.
It's okay. It's not a problem. I've been in many places, so it's fine. Yeah, so I'm Catarina Tiburzi. I'm currently at the Cagliari Astronomical Institute in Sardinia, Italy. I'm part of the European Pulsar Timing Array collaboration as Antoine, the mastermind here. So Antoine gave sort of some part of what I'm supposed to say today. So we're going to repeat some steps, but I guess repetita juvent. So I'm more on the side of the detectors, let's say, in pulsar timing array experiments. So I'm going to focus a bit more on that side. The detectors in our experiment are pulsars, in particular millisecond pulsars, and they are analyzed using a technique that is called the pulsar timing. So that's going to be the first thing. I'm going to tell you something again about pulsar timing arrays. What are we searching for? What kind of gravitational waves we are searching for? And that's where we tip into supermassive black hole binaries. And then, of course, as you know, there has been we cannot call it detection, but let's say the evidence for the 3 sigma gravitational waves from the 3 main collaborations of PTAs, and then a lot about the future, because I'm pretty sure that we are on the verge of the 5 sigma detection that we're searching for. So let's go. Pulsars, again, you all know what they are. They are the remnant of very massive stars after supernova core collapse. Pulsars are neutron stars in particular, and they are neutron stars that can be seen as basically galactic lighthouses. So they really act like a lighthouse. There are these beams of emission that are generated approximately above the magnetic poles of the star. This is a very zero order idea of what happens, but just to make a sense. These objects are fast rotating. The spin axis and the magnetic axis are misaligned. And so these 2 beams of emission that are mainly visible at radio frequencies are co-rotating with the stars. They are sweeping the space. And if the Earth is in the line of one of these 2 beams, an observer at Earth will receive 1 pulse of emission from every rotation of the star. So exactly like a lighthouse. The pulsars radiate, again, zero level, they radiate their own kinetic energy, their spinning energy, no? So you can imagine that given a certain period of the spin of a pulsar, then the pulsar in time will spin down because it emits its own kinetic energy. So we can build this very famous plot called the PP dot diagram, where we have the P dot, so the spin down, the spin down quantity on the y-axis, the spin quantity on the x-axis, and we can basically place all the pulsars that we know in this diagram, and you can see that they are basically naturally dividing into 2 big islands. One is the one that we call of the normal pulsars. They have a relatively high spin downs that mean that they are basically slowing down very fast, and they have relatively low spinning periods. Okay, so these are relatively young pulsars. And then we have this island here of the millisecond pulsars. The millisecond pulsars are pulsars that at some point in their life have been in a binary system, and they have accreted mass and particularly angular momentum from the companion. And so they spin down very fast. So the spin periods are extremely fast, in the order of the millisecond, creatively millisecond pulsar, millisecond periods. Their spin downs are very slow. So They spin very fast, they spin down very slow. For these characteristics and the fact that they are typically more massive than the normal pulsars, millisecond pulsars are very stable. Very stable in the pulsar jargon means that it is possible, or let's say, their pulses will arrive at Earth very regularly, while these ones might present some irregularities, this one not so much, let's say. So these one in particular are going to be the preferential sources for pulsar timing array experiments, given their stability. Okay, I thought I had the computer here. Okay, so how do we analyze a pulsar? There are of course many studies that you can do on pulsars, but the king of the pulsar analysis is through pulsar timing. In pulsar timing, in particular, you have, let's say, you take your favorite pulsar, you take your favorite telescope, you place someone to observe this pulsar at this telescope. And this person will observe a train of pulses. This is all zero level, cartoonish, etc. Will observe a train of pulses arriving at a certain time of arrival, TOA, time of arrival. Okay. So at this point you say, okay, I have this thing. I would like to know my pulsar a bit better. What do you do? So you start from a very a realistic set of what we call the ephemeris, an ensemble of characteristics with which you can paint your pulsar. The amount of the spin down, the amount of electrons between you and the pulsar, the position, etc. And you say, okay, given all of these properties, I build and keyfabe, so something happens here, and you can use this set of ephemeris to build a model of the time of arrivals. So you say, okay, I have the ephemeris, I use them in a black box, and I generate a model for the TOAs that I should be receiving if the pulsar has these characteristics. Then you say, okay, I have the model, I have the observations, I subtract one from the other, lo and behold, you have the residuals, what we call the timing residuals. If my ephemeris are good, then these timing residuals are gonna be, where is it? I don't have it, but they're gonna be white. So sort of Gaussianly distributed, no? So you did a good job, you have good ephemeris, you can predict your TOAs. What happens instead if you don't have good ephemeris, if you have something that in the ephemeris is wrong, right? Wrong, right? Your TOAs are not gonna be white. There are gonna be some structures inside. So this I'm cheating here, but follow me in this fable. You might have something like this. Here you have the residuals. Here you have the residuals in the y-axis. Here you have the time, and you can see that the residuals are following some kind of structures. So your ephemeris are terrible here. There is something very wrong because these residuals, I mean, clearly they are showing you that your model is bad, it's very bad. If you take the power spectrum of this stuff, you have something like this. So here you have the frequencies, and here you have the power. And you can see that there is a lot of power at the low frequencies. This is what we call a red spectrum, not a surprise for anyone. So in pulsar timing, when you have something like this, it can mean a lot of things. It can mean, of course, that your ephemeris is bad, but in this case, it is not exactly what it is that your ephemeris cannot predict everything, no? There are some things that are stochastic, you cannot predict them. In this case, a red spectrum of your timing residuals can be caused, for example, by a variable interstellar medium that is going to be something is our main enemy now. Some noise in the fact that your pulsar is spinning, maybe it has some irregularities and so on, can be planetary ephemeris that are incorrect, timing standards that are not correct, and possibly gravitational waves. And this is what we want, of course. So something like this might be caused by gravitational waves, right? Absolutely not. No. This is not because, but gravitational waves will cause some kind of red spectra. not like this because this is extreme and is only one pulsar. So let's have a look at the gravitational wave spectrum right now. We have here, I'm just placing the frequency of the gravitational waves and their power here, the terrain, sorry. We have a series of experiments that are covering the spectrum, ground-based interferometers, LISA, pulsar timing arrays, cosmic microwave background, etc. So we are with pulsar timing arrays, so the fact that gravitational waves might give red spectra in the residuals are focusing on gravitational waves in the order of the nanohertz. And in particular, here in pulsar timing arrays, the sources of the gravitational waves that can cause that kind of residuals are possibly supermassive black hole binaries. Supermassive black hole binaries are the main possible source causing gravitational waves in pulsars. These are the astrophysical sources, but there are other kind of sources that might be causing the same kind of effect, sort of the same kind of effect, but they are more cosmological. What we think is that likely the most important source of gravitational waves in PTA band is supermassive black hole binaries during their merger. Before the LISA band, so before they really collapse, so a bit further away with respect to where they would emit in the LISA band. So, okay. So let's assume now you have one pulsar, your favorite pulsar, very stable, beautiful pulsar. You have a source of gravitational waves, supermassive black hole binary somewhere before Z1.5. What is the kind of residuals that you expect? Not in the power, but in the time domain. You're gonna have something like this. So the characteristics of the gravitational waves of the source, of course, enter. So here we have the polarization angle. This is the angle between the gravitational wave source, the Earth and the pulsar, etc., etc. So here you can see that these kind of residuals, these are exactly the time domain residuals. They are basically represented by a sum of sines and cosines, given also two terms that we are referring to as the Earth term and the pulsar term. So this equation is not exactly the most up-to-date, as you can see, comes from 2004, but I think it's pretty explicative. It has a lot of problems. I mean, here you really exemplify all the problems that we have in PTAs using only one pulsar. Because first of all, this thing is full of sines and cosines. If you understand what happens in pulsar timing, where you have your observations, your ephemeris, the model, something that I missed to say is that to refine your model, you fit each parameter in the ephemeris, no? So of course, something like sines and cosines are the first thing that get absorbed. So this thing is gonna disappear completely. Second thing that is dramatic, here we have the distance between the Earth and the pulsar. That is something that absolutely we don't know. We have only one pulsar for which we know the distance with a precision less than 1 parsec. It's dramatic, this thing, no? Right. So long story short, we cannot use only one pulsar to search for gravitational waves. It's impossible. It's going to be a lost cause, okay? So not only one pulsar, and also a single gravitational wave is not going to fly. So at some point, people said, okay, not one pulsar, let's put an array of pulsars, okay? Okay, an array of pulsars, but still one single source that is going to be extremely faint. The amplitude is going to be extremely faint in pulsar timing. Again, it's not going to fly. So what do we do? Excuse me, I'm skipping a bit ahead. Forget, last 30 seconds, wipe it out. So again, if you look at something like this, sorry, rewind, take. So what do we do? we don't look for a single pulsar, we look for an array of pulsars. We don't look for a single supermassive black hole binaries, but we look for what we call the incoherent superposition of gravitational waves from the population of supermassive black hole binaries that galaxy evolution tells us there should be somewhere within a certain z, within a certain redshift, right? So we want to believe that. So what we are searching for is not one single supermassive black hole binaries, but the population and what we are calling the gravitational wave background, okay? A background of gravitational waves at nanohertz frequency in gravitational waves. So the strain of this gravitational wave background, this GWB, in the residuals of a certain pulsar, of one pulsar, is going to be something like this, where f, of course, is the frequency of the spectrum. And if you convert it in a pure power spectrum of the timing residuals, you can see that this is a power law, and the power law is extremely red, minus 13/3. So we go back to what we were saying here. Having a red spectrum might be a smoking gun for the presence of gravitational waves. Okay. So, closing up to what Antoine was saying, we cannot rely on the fact that we look just at the timing residuals, because as we said, they are extremely difficult to treat one by one. So what we do is to take the timing residuals of all our pulsars. We have an array of pulsars. We said, no, get an army of pulsars. We take their timing residuals and we correlate them pair by pair. And we build something like this. If there is a gravitational wave background caused by supermassive black hole binaries, very regular, circularly spiraling, etc., the correlation, the angular correlation, is something like this. This is the famous Helings and Downs curve. In the x-axis, you have the angular separation. In the y-axis, you have the correlation. And getting pairs by pairs, you take a pair of pulsar. What is the angular distance is this one. What is the correlation? The prediction is this one. You get this one, and you get the gravitational wave background at nanohertz frequencies. Good. Good. This is the theory. Where are we? We are in billions of collaborations now in the world that are searching for gravitational waves at nanohertz frequencies. There are an American collaboration, of course, the European one, the Australian, there are the South Africans now, the Indians and the Chinese. Sort of all together, except for the Chinese collaboration, we are converging into the international pulsar timing arrays, trying to put together all our timing residuals and getting to the detection of the GWB. Because by now, for example, this is currently on the side of the European pulsar timing arrays. In recent years, we joined the forces with the Indian PTAs, so we are let's say a consortium now, EPTA and INPTA. EPTA uses 5 by now 5 plus 6 plus 1 radio telescopes in Europe: Jodrell Bank, Westerbork, dismissed, Effesberg, the Sardinia, Nancy, and the interferometer among these 5 that is called the LEAP, the Large European Array for Pulsars. The Indian PTA uses GMRT and the UTI radio telescope. Again, where we are. For the European and in PTA, also this one was built only with the EPTA because of time reasons. We had a deadline to meet. For the EPTA, currently, this is what we get. This is what also Antoine was showing. Correlation in the y-axis, angular separation in the x, the prediction for the Helings and Downs curve, the orange violins are our calculations now. And this is a sort of a 3 sigma detection, 3.2, something like that. Are we happy with this? We are using 25 pulsars currently, and these are the last 10 years of data because that is where we have the best instruments in the telescopes. Are we happy with this? No, because what we want is a 5 sigma detection. We want to avoid false detections that are always behind the corner. So 3 sigma is not sufficient. It's barely sufficient to say that there is an evidence. And there are other problems, as he was saying. The amplitude of this signal is really loud, is way higher than what we thought. The spectrum is flatter than what we thought, and the thing is that all the collaborations are seeing the same. The one with the highest sigma, significance of the detection is Nanograph, the American collaboration, with something like 4 sigma. But we are all consistent in saying that the signal is louder and flatter than what we thought. So here there is, of course, there is a tension, there is a problem somewhere, and we still don't know where. Also because this is the only wall of text that I have. Also because there is not a lot that we can do at the moment. We cannot say whether the signal is astrophysical. If it is coming from supermassive black hole binaries, we cannot say if the signal is cosmological, if it's coming from something exotic like something exotic like strings or whatever you want to imagine. Because the spectrum is not characterized well enough. We know that if the source is cosmological, if the source is astrophysical, so supermassive black hole binaries, the spectrum should not be very smooth, because at some point we should have like maybe a very loud supermassive black hole binary that is cracking the spectrum. We cannot say anything. The spectrum cannot be constrained right now, so we still need to work. Again, I encourage you to not take this as a detection, because there is an evidence, there is not a detection. Well, nicely enough, this is again the European PTA collaboration. We were awarded with the RAS prize this year. This was very nice. We have a very big collaboration. As I said, we are connecting with the INPTA, the Indian PTA. We have a lot of young people. One of my closest friends and colleague was collaborating with Nicola on the early career scientist gravitational wave community. We are really trying to get the better that we can on these things. It's difficult, but I think that we are trying to do our best. And now a look in the future. This is currently more or less where we are. I mean, we, let's say, published, there is not much more than that. Let's have a look at the EPTA now. As I said, in the EPTA, we have this 6 telescope 5+1 with Westerbork that has just been decommissioned. And Westerbork was the only low frequency telescope that we had in Europe. That's also one of the reasons why we are partnering with the Indians, because they have GMRT, the upgraded GMRT that is a super good telescope now, going to P-band, etc. But currently, we are really doing an effort to add a couple of European telescopes, a couple of cutting-edge European telescopes that are LOFAR, the Low Frequency Interferometer, and NENUFAR here in France at the Nancy Radio Observatory. In particular, LOFAR is as I said, is an European interferometer. The modules are scattered all around Europe, and each module is looks like this. This is the beautiful Beer station in Ireland. We call them station. Each module is called station. You can see that there are 2 fields of antenna, what we call the high band antenna, these sort of big boxes here, and the low band antenna, these sort of hanging racks here. The high band antennae work between 100 and 240 megahertz, low band antennae below 100 megahertz. Keep into account that the majority of the PTA collaborations are working at L band, one order of magnitude of frequency more, 1.4 gigahertz. So these are really an asset, and I think as Europeans, we should really look towards these instruments because they are, for how they are working for pulsars and gravitational waves search, they are really unique in the world. Concerning LOFAR again, there are, this is a bit the distribution of the stations. So we have the majority in the Netherlands, 6 in Germany, 1 in France, 1 in Italy is going to be built, etc., etc. So we are touching really upon all Europe. We are extending also east. And then there is this magnificent instrument, our partner that is basically recovering very good bandwidth, bandpass in below 100 megahertz. Nenofar is magnificent. I cannot have words to describe how Nenofar is working. It's fantastic. LOFAR started working in more or less 2012, 2013. We have been using LOFAR since then. We have been monitoring a lot of pulsars weekly, so we have a gigantic amount of data. Nenofar has been starting. Nenofar started in 2019, so also there we have now 5-6 years of data. So, yeah, I mean, they haven't been included in the European PTA dataset yet. It was about time that someone was taking this burden, and I was lucky enough that my student could do it. Why are we focusing on instruments like this? Why they are important? If you remember, looking at this thing, the fact that we had this kind of structures in the timing residuals and the power spectra that are red, I said that something that is generating this kind of things can be also the interstellar medium. As a matter of fact, the interstellar medium is one of the 2 main competitors for gravitational waves nowadays. So there are 2 things with which we have the majority of problems. One is the interstellar medium, mainly what we call the dispersion noise, and the other one is, of course, the fact that pulsars are not exactly super stable. They have, of course, irregularities. So interstellar medium and in particular plasma are causing something that is called, as I was mentioning, DM noise, dispersion noise. Dispersion noise comes from a phenomenon called dispersion, where the pulsar is emitting broadband radiation at the pulsar site, and then, let's say, when the radiation crosses through a plasma, the radiation is delayed with a frequency dependency. In particular, the delay, delta T, is inversely proportional to the frequency squared of the radiation, not the gravitational waves, and directly dependent on this parameter called dispersion measure, that is basically the column density of free electrons. Note that dm is a parameter that is in the ephemeris and it is fixed. So this is the problem, because pulsars are very high moving objects, and so the line of sight is spanning through different kind of interstellar mediums while you're following the pulsar. So if your dm is fixed and your dm in reality is moving, it means that your residuals are going to suffer for it. So at some point the residual is going down, at some point is going up, etc. And so you're going to end up with the red noise. This is what we call the dispersion noise. So to keep care of this, typically we try to model the spectrum in a Bayesian in a Bayesian-based fashion. But as I was mentioning, the bulk of PTA data are at L band, and at L band you have a very unfortunate situation because the dispersion is visible, creates noise, but is not large enough to be calculated. So you are in a lose-lose situation, no? So what do? You go at low frequencies, you add the low frequencies, radio frequencies, because This is a bit complicated as a plot now. But at low frequencies, the fact that the dispersion noise is inversely proportional to the frequency squared is an asset, because the magnitude of the dispersion is gigantic, and so you can calculate it very precisely. So recently we are trying to update the DR2, the second data release of the EPTA, with LOFAR and NENOFAR data. This is a work that is led by my PhD student, Francesco Iraci. We have 12 pulsars for which we have data at low frequencies among the 25 pulsars that we have in the sample. And the results are really striking. This is just a family portrait where you have the results from the Bayesian analysis for this modeling of the DM noise, the amplitude of the DM noise here, the spectral index of the DM noise. In orange, you have the results from the DR2, so the one for which we went into designing that beautiful helix and downs curve. In blue are the results from the new analysis. So you can see how in certain cases, look at this one, for example, the corner plot is shrinking from something completely unconstrained as this one to something like this. So, of course, it is making a difference. We are grazing toward the publication. That is also causing other problems, of course, because you are going to see also all the issues that your models have. Of course, if you have bad data, you can fit whatever you want in that data. If you have very precise data, then your model are starting to crack. So that is something that we are currently looking into now. The problem of the solar wind, that is another plasma causing possibly correlated structures in our timing residuals. But what we are trying to do now is also running towards the third data release that is going to include 60 pulsars in the EPTA, so from 25 to 60 pulsars, including also the low frequency pulsars from LOFAR and NENOFAR. This is something led by one of our this person who is looking after the early career scientist, Golam Shaifullah, at the University of Milano Bicocca, who is also working for the IPTA DR3. And with the IPTA DR3, we are pretty confident that there is going to be the 5 sigma detection, we hope. And that's all. Thank you.
Thanks a lot, Catarina. So we have time for a few questions.
I was signing 32 minutes, so but, okay.
Yeah.
So a very nice talk, thank you. So my ignorance here, you said that you go to lower frequencies. So the point is that because you increase the delay between the different wavelengths. This is the first thing, and the band is large enough to have more wavelength to compare. This is the point.
The point is that having this effect of dispersion that is inversely proportional to frequency squared. If you have the low frequencies and you have a bandwidth of, say, even 100 megahertz, not a lot, but if you compare the delays, this delta t that is being caused by the dispersion between the top of the band and the bottom of the band of these low frequency instruments, and the same thing at L band, what happens at the low frequencies is that the delay becomes huge. And when you have a delay that is so huge, the fit that you can do, the calculations that you can do about this kind of delay is extremely precise. And so you can apply that kind of delay to the high frequencies and then correct for this effect with incomparable.
When you say huge, so a low frequency compares to the L band, can you give me a number? Because you say huge, like it's microseconds in. I don't know on the plot.
No, it's way more than milliseconds.
Okay.
Yeah.
While
yeah.
in the L band, it's much smaller.
Yeah, I have a nice picture, but I don't have it here. But if you compare, for example, say a variation of the DM. The DM is calculated in a very strange unit of measure that is a parsec per centimeter cube. You don't ask me why they chose that. Say a variation of DM of 10 to the minus 3. That is a very typical difference in DM between observation and observation. At L band is going to be something in the order of, I don't know, 2 milliseconds, say. At our frequencies, the 140 of LOFAR is going to be tens and tens and tens of milliseconds. So it's clear that when you have such a gigantic swipe, the fit is order of magnitudes more precise.
Thank you.
Thank you. Another question for Catarina? Yeah.
I have a technical curiosity, actually. What about the Medicina radio telescope, the Northern Cross, and Noto?
I've been banging the door for the Northern Cross because the Northern Cross would have a magnificent central frequency. The Northern Cross in Medicina Bologna there is this historical used, not historical because it has been founded many years ago. Radio observatory where there are a few instruments, including the Northern Cross, that is this gigantic interferometer, was central frequencies around 300, 400 megahertz, 350 P band in any case. That band is magnificent. I think it would be even better than ours for a lot of technical reasons. The problem is that the bandwidth is 16 megahertz. That is, it's impossible to use it for pulsar timing. LOFAR has, the quantity that you have to look is what we call the fractional bandwidth. And the fractional bandwidth basically is central frequency divided by bandwidth. The larger that is, the better that is. So for example, for LOFAR is 0.6. For Nancy is 0.2, something like that. So Medicina, unfortunately, has the problem that, yeah, the central frequency is 300, but the fractional bandwidth is 60 megahertz, where LOFAR has 100, NENOFAR has 100. 116 is not enough. And I've really asked a lot of people if we could think to increase the bandwidth. It's impossible because as an interferometer is really heavy. And the other, the 32 meter in Medicina and Noto, I suspect that the sensitivity would not be good enough because, like, for example, the smallest telescope that we have in Europe is Sardinia. Radio telescope is 64. The biggest is Nancy and Effesberg 100, and the equivalent for Nancy is 96. 32, I suspect, is not enough, in my opinion. Then I don't know. I mean, we could think to do it. Noto is the same. We could think to try to see what we can do. In my opinion, there is not a lot of room. My personal take.
Thank you, Catarina. We have time for a last question.
Yeah, in the same vein, I was actually wondering, are there any potential pulsars that we could add to the pulsars that have followed for the PTA? And yeah, first of all, can they be identified and will that actually help?
Yeah, so of course the number of pulsars is very important because, as you can imagine, when you want to cover the links and downs curve, here. So the links and downs curve here has the angular separation between the pulsars. So the more pulsar pair you have separated, close, etc., the better it is. I think the number of pulsars is actually the most important parameter in the sensitivity, given a study of a few years ago from Avi Siemens. Maybe now, I don't know, maybe now there are some modifications, but I don't know. As I said, the EPTA has 25. They did a lot of calculations, not me, but some former PhD of mine and so on. They did a lot of calculation on why to choose only 25, and it was because of the amount of sensitivity that you would gain in the links and downs curve. We are going to have 60 with DR3. Nanograv has like 80 or so, right there. IPTA 100 and Whistles. So it is always good to add the pulsars. The important thing is that you add pulsars with some criterion. So you need to be sure that their timing residuals, the noise, the RMS is at least below 1 microsecond. Typically, just count that in the simulations, we always assume a standard noise of 100 nanoseconds that I've been always against because it's completely impossible. And so I've used it myself, but I was young. And you need to have some criterion. So you have to study the pulsar quite some years. You cannot add pulsars that have just been discovered and observe 1 year and just go. You have to be sure that at least the RMS is below 1 microsecond. The better you know it, the better it is. So yeah, surveys are important, but it is extremely important that you study your things. So after that, that you collect all the little figures. Then you have to study them. Otherwise, you risk to add noise.
Okay, thanks a lot, Catarina. So we have to stop now.